All right, so today we're going to talk about direction fields, which you have some experience with direction fields. So there isn't anything new here as far as direction fields go. I'll make just a couple of comments regarding them and Euler's method. Now, I'm going to start off with Euler's method. So let's just quickly kind of describe what Euler's method is. We've done something similar to Euler's method in this class. However, Euler's method is a better approach to what we've done. So Euler's method is used to approximate values of differential equations. Or to be more specific, when we say the values, we would say of solutions of differential equations. So basically, Euler's method is something similar to what we did earlier on in this class. Like if you remember earlier in this class, we kind of had a curve and we said, look, at this point, at this x value, what's the y value of that point? And we noticed finding that y value, that solution, was a difficult value to find. But what we noticed is if we found another x value where the y value of this function was easy to find, we use that, and then we use the equation of the tangent line, and the y value of the tangent line was used to approximate the y value of that curve. If you remember, this was called linearization. So Euler's method does something similar to that, except it actually is more accurate. So what Euler's method does is it says, look, when you move down this tangent line, okay, the further you go away from the point of tangency, the approximations of the tangent line aren't as good. They're not good approximations because you could notice how far it is from the actual curve. So what Euler's method says is, look, why don't we still use the equation of the tangent line or the derivative, but update the slope? Because what do I notice? As I move along this curve, what happens to the slopes of the tangent lines? They become steeper and steeper and steeper. So with that said, like let's say if I want to approximate this y value, okay, and I can't find an easy way of just plugging in this x value into the function because it's complicated. So I want to kind of approximate this y value, and we notice like let's pretend that the point that I could find an easy y value for is this. And what you notice is linearization fails to be that successful here, because if I use the equation of the tangent line, you could see that at this x value, the y value of the tangent line is way off. So what Euler's method does is it says, look, why don't we create step sizes? Okay, like for example, in this one, we'll take step sizes of 2. So what does that mean? In 2 steps, I should get from this x value to that x value. So let's call this x1. And then what would be step 1? Step 1 would be this, x2, and then x3. Or we can call this x sub 0, and then x sub 1 and x sub 2. Okay, so why is this in 2 steps? It's because from here to here and from here to here. So the way Euler's method works is, so I'm just going to give you a basic description of it, and then I'll give you kind of like the formula that we're going to use. It says, look, don't worry about the y value there. What we want to do is we want to find the equation of the tangent line and use the tangent line to find the y value at that x value. Okay, and then what you notice is we say, okay, look, now that we're here, what we notice is now I could use the slope of this the tangent line to this curve here, which what do you notice about the slope of the tangent line here? It's actually steeper. So what we're saying is using the slope of that tangent line from here, we can go from x1 to x2, which what does that do? When I updated my slope, see, the slope of the tangent wasn't as steep as it was here. So when I stopped here, I said, okay, now I'm going to use the slope of this tangent line, and I'm going to go up. So whatever my step size is, I'm going to multiply to this y value, which along with the slope, which is going to give me that. So notice how this approximation is actually putting me closer to the actual solution rather than me using just a single tangent line. Now, how do you think we'd get even a more accurate approximation? And I'm sure you guessed it, we would have more step sizes. So in other words, if we have this curve again, and let's say this is x sub 2, and this is x sub 0, if I break this up into 4 steps, so it'll be 1, so it'll be 1, 2, 3, 4. So what would happen is I would use this slope. I would go until x sub 0 to x sub 1. And then here, I would use the slope of this line, which would kind of be slightly steeper than that. And then I would use the slope of the line to this curve there, which would become even steeper. And then I would use that slope, which becomes steeper. So what do you notice? It's kind of like we're updating the slopes of the tangent lines, which is getting us closer and closer to the actual y value. So basically, with that said, we're literally just using the equation of the tangent line, or more importantly, we're really just using the slope of the tangent line, which the slope of the tangent line is simply found by the derivative. So, for example, what we could say is the following. So here's how Euler's method works. Let's kind of summarize it this way. We could say, suppose we have a point on the curve, which is x sub 0, y sub 0. Okay, and what's our goal? Our goal is, or we could say we are given the derivative or the differential equation, which in other words, the differential equation is pretty much the derivative, right, of a function, and we are asked to find its solution at x sub n comma y sub n. So it's kind of like basically saying we start from here and I want to somehow get to this value, which that point has coordinates x sub n comma y sub n. So what we're going to do is we're going to say this. We're going to say, okay, look, the first thing we need to decide are the step sizes. Okay, and of course, the step sizes will depend on how many iterations we want to do to get to x sub n. So here's what's going to happen. We're going to say y sub 1, which is going to be our first approximation, is equal to what? Y sub 0. So this is the value, the y value. So if I were to draw this out, here's what we're saying. If we start here, that point has coordinates what? X sub 0 comma y sub 0. Now, if I want to kind of, whatever my step size is, let's call the size of the step size h. Okay, so that'll be the size of the step size. So then, if I want to go from here to here, what is that going to be? That's going to be x sub 1 comma y sub 1. So to find y sub 1, what do I need? Well, I need y sub 0, right? That's why I start from this y value, and I need to add kind of the change in this y value. So what is the change in that y value? Well, isn't it basically, if I know the step size, if I'm moving over h units to the right, then what will tell me how much to move up? Won't it be the slope of that tangent line? Because after all, this is the slope of the tangent line. So what I need to do is I'll just say plus h, which is how much my run, times capital F of x sub 0, y sub 0. And see, capital F, we would call this the differential equation. So that's basically the derivative. So of course, what we could say slash, that's the what? Slope of tangent line. So what that basically says is, look, we start with this y value. That's our starting point. This is my run. When I multiply to the slope, h times the slope of the tangent line will give me what the rise is. So when I add this to y sub 0, that'll put me at y sub 1. So then how do I get to y sub 2? Well, now I'm using this slope, right? The slope. The slope of the tangent line to that curve over there at x1, y1 to get to y2, which is x2, y2. So you could see, you'd say, okay, well then y sub 2 would be what? Y sub 1 plus your step size times the slope of the tangent line at x1 comma y1, which is basically that slope, right? Because if I have x1, y1, I could plug that into the differential equation. That'll give me the slope. The run times the slope will give me the rise, okay? And then we keep going. And if we keep going, what would I do until I get to the nth one? The nth one would be y sub n minus 1 plus h times f of x sub n minus 1 comma y sub n minus 1. And that would get us to the final one. Okay, so remember, the step size, your h, so remember, this is your slope of tangent line, which is literally the different, you're using the differential equation. This is your step size, or in other words, delta x, right? It's how much you're changing x. And this is the y value you were at, okay? So this is the y value of the n minus 1 term. Okay, so if you keep this process, so look, this is almost the same thing as linearization, except what are you doing? We're just updating our slope, which basically gives us a better approximation. So instead of using a single line, we're kind of breaking it up and we're using multiple lines and getting it to be steeper and steeper and steeper. So when you update your slope, what's the advantage of that? These approximations are still off, but they're actually closer than they would be if we just used a single line. Okay, so let's look at an example. We're going to say use Euler's method with step size 0.1 to construct or to approximate values for the solution of y prime equals to x plus y and y sub 0 equals to 1. Okay, so basically what we're doing is now we're using this to approximate the y values of the solution. So what we have here is they give us the initial condition. So what do we know? Whatever this function is, when x is 0, y is 1. So in other words, what do we know? X sub 0 equals to 0 and y sub 0 equals to 1. So that's kind of like our first or our given point. So what does that mean? If I move, and if my step size is 0.1, what do we know? H is 0.1, okay? And if H is 0.1, what does that mean? We're gonna move over 0.1 to the right. So here's what we're saying. So if I were to find y sub 1, and this is an approximation, so this would equal to y sub 0 plus H of f x sub 0, y sub 0. So what do I need to do? This becomes y sub 0 is just 1 plus h is my step size, which is 0.1 times this is what my differential equation. So how do I find y prime, or the slope of the tangent line? I plug in 0 for x and 1 for y. So for this one, we would say, let me come off to the side, capital F of 0 comma 1 equals to 0 plus 1, which is 1. So this becomes 1, which that becomes 1 plus 0.1. So that's 1.1. So what does that mean? That means what we're saying is the solution to this differential equation would have, if I move 0.1 to the right from 0, right? Because when x is 0, I move 0.1 to the right. Now x is what? 0.1. The y value will be 1.1. So what are we saying? Now, this is an approximation. We're saying, look, if x is 0, y is 1, then we're approximating that if x is 0.1, I've moved 0.1 to the right, then y is 1.1. So what would y sub 2 be? The process is the same, right? Except now, what do I need? I need y sub 1 plus h f of x sub 1 comma y sub 1. So what does that equal to? That becomes y sub 1 would be 1.1 plus 0.1 times, now if I plug in capital F of 0.1 comma 1.1, what does that become? That's 0.1 plus 1.1, which is 1.2. So if I plug in 1.2 here, what does that mean? I get 1.22. So what is this saying? The solution to this differential equation, when my x value is now what? From 0.1, I moved another 0.1 to the right, is what? When it's 0.2, the y value will be about 1.22. Okay, and so on. And so you could see if I were to do y sub 3, then what would that mean? I would have y sub 2 plus h of f of x sub 2 comma y sub 2, which would be 1.22 plus 0.1 times, and if you were to plug, what would this be? F of 0.2 comma 1.22, which would be 0.2 plus 1.22, which would be 1.42, and that ends up being 1.362. So in other words, what are we saying? We're approximating and saying when x is 0.3 for the solution for this differential equation, when x is 0.3, y is about 1.362. Okay, so, and we'll stop there, and we could keep going forever, right? But remember, how do I get a better approximation? Make your step size even smaller, okay? So sometimes we have to understand and see what if this question, I could have also changed this question up saying approximate the value for the solution of this guy when, I don't know, we could say x equals to 0.4. So what does that mean? I had to keep going one more time, right? Because now I got to x equals to 0.3. So if we want to approximate it when x equals to 0.4, I would have to go one more step size. Okay, but remember, the smaller the step sizes, the more accurate these approximations are. Okay, so the last thing I want to talk about is kind of what we've done before, which is direction fields. Okay, the one thing I want to kind of comment on, we know that direction fields, like you're given a differential equation, right? And then whatever that differential equation is, like for example, y prime equals to x plus y, like the one we did earlier, see, we could create a direction field for this because remember, what is the direction field composed of? You just plug in all the x and y values, and then whatever the slope is, you just draw the slopes. So let's forget about this for now. What I want to talk about is something that the book mentions, which is called an equilibrium solution. So if let's say you have something, a direction field that looks like this, okay, so whatever this differential equation looks like, see, what is an equilibrium solution? Well, we always follow the direction field depending on where we are, right? So if let's say if I pick a point here and I say sketch the graph of the solution to this differential equation using the direction field, you'd say, well, if this is the point, if I move along this point, what do the slopes of the tangent lines tell me? They tell me to go up, and then it says, oh, it settles down, and it kind of goes to this because why do we know that it settles down here? Because these are horizontal tangent lines, and it goes kind of like this. So what are my equilibrium solutions if I'm up here? There's two equilibrium solutions. If I go this way, whatever this y value is, right, this is an equilibrium solution, and then also this is an equilibrium solution. So think about it this way, like if this was y equals 4 and y equals -3, if the point is here, my equilibrium solutions are y equals 4 and -3. Why are they called equilibrium solutions? Because it settles down to those y values. Now look, if I were down here, I would have only one equilibrium solution, because from here, what do my direction fields tell me? They tell me to just go up, and then when I get to this horizontal tangents, that's where it's equilibrium. So depending on where you are will change what your equilibrium solution is, okay? So I trust that we all remember how to make direction fields. I'm not going to spend time talking about them, but if you have questions about them, feel free to kind of talk to me, later on. But just to kind of also just wrap this up real quick, remember, what's the difference between Euler's method and the linearization? For linearization, we basically did this. We said, look, use x sub 0 and use it to approximate x sub 1. Linearization did this. It just used the tangent line, and it said this is the y value, and that's the solution of that curve right there. But Euler's method, what does Euler's method do? It says, look, we could do better than this. Let's break this up into step sizes. And then the step sizes do what? Like, so I broke it up into, in this case, 1, 2, 3, 4, 5, 6 step sizes. So what do we do at each step size? We update the slope of the tangent line. And what do you notice when you update the slope of the tangent line? It stays closer to the curve. Now, of course, the more step sizes, the better off your approximations will be. And see, through linearization, we only get one solution, but through Euler's method, at each step size, we can actually approximate the y value of the curve as we kind of wrap around it. Okay, so Euler's method, linearization, they have their similarities, and of course, they have a lot of major differences. Okay, and Euler's method is actually more accurate in solving these, or is more accurate in these approximations rather than using just an equation of a tangent line, just using linearization. Okay, so if you have any questions, feel free to ask me. I'll be more than happy to help you out.